Well, one philosophical problem of time is you've got this manifest image of time. I don't think of this as what's directly experienced, but rather I borrow this term from Sellers of manifest versus scientific or physical. As our kind of common sense theory of the world. Maybe yours is different from mine. People, around the edges, they're going to differ a little bit. But generally people have this idea that there's, this privilege now. Part of that is also this division of the world into these global tripartite structure of past, present, and future. So we tend to naively think of the past, present, and future as, these big global different things, which sectors of the universe which differ. You might add more. Maybe you think the past is settled and the future is open, and you can spell that out in some way. And then that tripartite structure is supposed to update itself in some way. So philosophers call this tense. And then, that tense is supposed to give you this flow. A separate thing would be a kind of directionality. The updating might be in a certain direction, but you could certainly have a manifold with a preferred direction without all that tense structure. So that I would want to distinguish those two things. There's also the view, which I'm going to talk about a little bit, which is the idea that one state of the world produces the next state, determines the next state, and that determination happens in time. Okay. Maybe your conception of manifest time is one where it's the flowing is continuous. Maybe it's discrete. It depends. Or maybe it even gets so fine-grained that you think it's independent of matter. So you think this flow of time or time is independent of matter. So some of and you could think of other features that you might want to add to this list. Now, when we look at physical time, well, of course, there's no one theory of physics. We've got quantum mechanics, relativity, and then various possible quantum gravitational theories. And all sorts of things. But still, let me make the general claim. On any of those theories, some of these guys are going to get left out. Right? So now it's a matter of dispute as to which ones get left out, which ones don't. The ones that get left out, to the degree that you think they're really serious things that you don't want to explain away, you might want to go and try to explain. And so one of my projects that I'm not going to talk about today is to try to explain why creatures like us would employ this kind of tense structure, treat the now different than the here, and appeal to various cognitive mechanisms, various features of physics, and various features of our environment to try to explain why it is that even though this stuff isn't, it seems that way to us. And you can do that kind of task with a variety of these things. And I don't think of it, again, as trying to deduce from physics some experience. That would be to solve the mind-body problem. You haven't deduced any experiential state from physics. Rather, I think of it more along the lines of Eddington's two tables. You've got the solid table, the solid macroscopic table. You've got the microscopic thing, which is not solid. But you can give an explanation from physics of why it would seem like it was solid, to a macroscopic organism. And so I would want to do similar sorts of things. So we have this. So there are conflicts and conflicts, or there are various ways in which they conflict. Some more serious than others. It's sort of like I can remember, an analogy is maybe long, like a lifetime ago when I was dating. Back before, so those of you dating now or young, now I think it's all electronic and you just friend somebody and something and then, but back in the old days you were in a bar or something and you had to look this prospective person in the eye. Now they would, in particular me, they would ignore, right? And so, but now there is ignoring and ignoring. Right? There's ignoring where they catch your eye, and boom, the head turns really fast, and it's sort of ignoring with extreme prejudice. And so the answer is no. You don't have to go. In the other case, they turn, but maybe there's a little bit of hope there. And in some cases, that would be the case. Okay, one case, my wife, but that was, so you would have some hope there. And so it's the same sort of thing with the just conflict here. You would have ignoring and ignoring. So in some cases you might think, well, okay, so suppose we take as an example Newtonian physics, and we look at the temporal structure of Newtonian physics. Well, there are all these different formulations, Hamiltonian, Lagrangian, Hamilton-Jacobi and whatnot, but generally you've got a one-dimensional manifold with a metric, given the duration, separate time metric from the space metric, call it G. Sometimes people put an order relation. I prefer betweenness because the theory is time reversal invariant, so it just defines betweenness between events. And so you can define betweenness like Birkhoff did as just a weakening of this order or that order. If you want to pull out betweenness. Then you can pull out other, and of course, preferred simultaneity structure. And time is the linearly ordered quotient set of the similarity relation. Now, if you look at this, you can just go and tick off. Is there a privilege now? Well, no, right? There's no, there's no nowness variable here. None of these hyperplanes are standing out as special. So, nope. Past, present, future, nope. Flow, because that presupposes that, no. Direction, no. Production, well, I haven't said what production is, so maybe. Continuous, yes. Independent matter, yes. You can just go down and do this kind of checklist. On the other, but getting back to the ignoring bit, there's ignoring with hope, where if you were a fan of this, you might say, well, what I needed was a preferred foliation for this sort of thing to make sense. Newtonian physics, I've got the preferred foliation. If I thought of the preferred foliation as a necessary but insufficient condition for having this kind of thing, I might think, well, I've got at least a necessary but insufficient condition for this, and so there's at least hope. On the other hand, it might be, depending again on what you think is in manifest time, it might be that there just isn't, that physics just explicitly identifies that feature and says no. Okay, so for instance, I don't think people have talked about this too much in the philosophical literature, but just as a kind of an aside, suppose we were looking at Newtonian gravitational theory, and you were doing it in the Newton-Cartan version. Well, then you absorb the gravitational force into the space-time structure, and you take, so what was the gravitational potential, there should be a G in there, goes to where I've got the potential depending on the distribution, so I've got the force formulation. I absorb that into the gravity, into the curvature. The space is flat, but the time is curved. So here I have my time metric. And if this is the distribution of matter, then the ticking of the clock is dependent on the matter distribution. So if I go over here, I've been affected ever so slightly, the ticking of the clock. And then if I thought that it was the ticking of the clock, the master clock of the universe was independent of the matter, then, well, no, it's not. It says, if you were using that sort of theory, then the answer would be no. Incidentally, as a footnote to that, Gödel has a famous argument from general relativity that says that the lapse of time is independent of the distribution of matter. It's kind of interesting that you could, at least in some formulations, repeat that argument even in classical physics. Okay, so now we're all, well, maybe I'll leave that. So we're all now familiar with the threat to a lot of this coming from relativity. Right, so there's a standard argument, which at least in the philosophical literature traces back to Hilary Putnam, and he supposes that somebody who was an advocate of this, who thought that this was real, the tense structure here, if he thought that was real, and used the natural Minkowski coordinates and identified the nows with the t equals constant slices, then it's a kind of reductio where you say, suppose you and I, we cross in the street, and then we draw out the simultaneity planes for each of us, do the relativity of simultaneity, and then draw those on what happens in, say, on some planet in Andromeda, and then you get these different points. And so what's real for us at this intersection differs between depending on which one we are. So which one is the so if you thought that, for instance, the future was unreal, then the question would be which future, this one or that one. And so you'd have these, and so you could do a kind of, if you wanted, you could do a kind of think of it as a kind of coloring argument where you color in all the events that are real, assuming that they're at least somebody else is real, some other event is real, and then start drawing in lines and coloring it and making doing a kind of reductio of the idea that the future is real. Unreal. That view is so alien to me. I'm just really reporting and not describing. So I sometimes slip up between whether the future is real or unreal. Now, some people have complained that that's a coordinate-dependent definition, but I think that's a misunderstanding of the argument. It's supposed to be a reductio of a particular position. The person who has that position can put in whatever events they want. They could just grab whatever events they want as the real ones, what they consider to be the real ones, and then we could run the argument. So we could use some other coordinatization and pick out some other t equals constant slices, and then we could get the same kind of trouble. Indeed, you could get the same kind of trouble, if you just, you could just, so there are all these, in the philosophical literature, there are all these little no-go theorems and stuff about that, where you give certain assumptions about what's in manifest time, and then you prove that you can't have that in relativity. And if you increase the number of properties here, you can just think of tons of them. So just off the top of your head, you could just grab some and say, well, if it's supposed to be global and actually matter to the physics, maybe be metrical, then you could say, well, the two temporal structures in relativity are the coordinate time and the proper time. Proper time's not global, coordinate time's not metrical. Then you don't have anything. But at the end of the day, I don't think these arguments are interesting, but what's really doing the work, the physics can't actually give you a kind of no-go theorem that you can't have some of these things, because you can always add structure, right? So it's really physics providing a certain setting with certain structure, and then methodology is really doing the rest, where you're then saying, well, show me why I need to add more if I need to add more. So you could add a privileged cosmic time or something like this, but do I really need to add that is the challenge. And so the challenge is really more methodological than coming straight from the physics. Okay. What time am I supposed to end? 15? Okay, good. Okay, so what I want to talk about, so despite all these challenges from relativity and how counterintuitive relativity is to our manifest image of the world, notice that some bits still survive. So when you go to relativity, it's still the case that, okay, you can grab all these different hyperplanes, but still, you can still think of, generally, you can still think of the world as one global spatial hypersurface determining the next, right? So I can still think of the world is evolving. I can decompose that 4D picture into a 3+1 and think of that one thing as pushing forward the next and determining the next. And so there's still this aspect of the manifest time that's still there in relativity. And that's what, and so I'll call that production. This productive picture where I can take some spatial hyperplane and then push forward. Now I can push forward in different arbitrary, as long as they're time-like directions, and get the next hypersurface at some later time. Well, okay, let me say a couple things about this. First, let me say one thing kind of philosophical and one thing about what's going on here in general relativity. first, I'm thinking, so you have this, there's this notion of production where one state is determining the next, and some philosophers have talked about that, and I think, so I think just to put some kind of philosophical flesh to sort of build up the picture here, you can think of various things people have said. So the philosopher Michael Tooley talks about the direction of causation giving the direction of time. So what one state of the universe is causing the next, he thinks, and giving the direction of time. Tim has a view somewhat. Tim Maudlin has a view somewhat like this, I think, where the laws, the real laws, are determining the next state, and so there's this connection between the laws, the direction of the evolution, and time. Okay, I think I have a quote. I wrote down a quote. So this is a quote from Tim. The passage of time underwrites claims about one state coming out of or being produced from another, while a generic spatial asymmetry would not underwrite such locutions. And here's another philosopher, Barry Lower, reporting on Tim's view, what he calls M laws, so the Maudlin laws, he's imagining the dynamical laws, and M time are made for each other. What he means is that the M arrows, the direction, the time arrows are tell the M laws the direction in which to produce the next state, and the M laws explain the passage of time. Now, what I'm going to say isn't really going to challenge this view. I think there are many responses, but still, I think it's an interesting consideration, what I'm about to start talking about. But first, what I want to say is that relativity, at least in some sense, allows still this picture, because, especially if you think, what's the ultimate in production? The ultimate in production is determinism. What's the ultimate in determinism? Well, a well-posed initial value problem. We've got existence, uniqueness, and continuous dependence of later solutions on the initial data. Well, now it's not true, of course, in general relativity that I can do this, that I have well-posed initial value problems, especially if you think of weird spacetimes like Gödel spacetime, where I can't even get a global, entirely space-like hypersurface at all. But people like to throw those away, which is unfortunate because they're beautiful. But people like to throw those away, and you can, if you restrict yourself to globally hyperbolic spacetimes, well, then you can prove a whole bunch of neat theorems. So Garrosh proved all these theorems in the 70s, where you're linking, having a Cauchy surface where each state, so the no closed time-like curves, each world line intersects the state once and only once, and the existence of a time function. And if you have a well-posed problem, then you've got then he's got a theorem where it's a Cauchy surface. And so if you have put data on, and in relativity now we're talking about a metric, a Lorentzian metric with signature plus, let's use minus plus. And so I'm putting data always on a plus surface, and I'm evolving, and I'm pushing it forward into the minus direction, right? When I'm doing when I'm getting that well-posed problem. Okay, so you could say, it might be tempting to say that, okay, manifest time takes a beating from relativity, but still I've got a little bit of manifest time left because I can still do at least this. So it's true, I can, different surfaces, so I would decompose, sorry, I should say, when you do the initial value problem, of course, you're decomposing from the 4D version to a 3+1, like Dirac's or ADM, and I'm putting data on a spatial metric, 3 metric, and the extrinsic curvature as the, like the initial position and momentum, and pushing forward and getting that for the later state. In the vacuum case, I've got four equations, elliptic equations to solve on the surface, and then I've got the 6 to evolutionary ones going forward. So in some sense, this manifest time is still there, well, parts of it. Well, now what about if I put the data on a null-like surface? Okay, so now to many of you, so this is many of you, this is old hat. I've never seen a philosopher of time mention it before, but to many of you, if you do numerical relativity, then it's old hat. Some of you interested in holographic principle will have thought about this and worked on it, and maybe be able to answer some of the questions I have about it. And it was developed in the 60s, Sachs, Bondi, Penrose, and it comes in different formulations. But the idea is to put data, instead of on a space-like surface, put it on a null surface. I think this is interesting if we think about it philosophically, because and so I'll describe a couple of those. There's all sorts of different formulations. So there's the tetrad one and a metric one. I haven't studied the tetrad one yet, but the metric one itself comes in various different forms. You could put the data on a light cone. This isn't that popular because of that point. You could put it, the more popular version is you grab a space-like 2 surface, and then imagine null-like vectors going out from it in a kind of foliation into these wedges. So it's called the 2 + 2 formulation. And so if you like, you can imagine these as touching up against the sides of the light cone, right? And so you can do this kind of 2 + 2 formulation. There's also one where you do one is light-like, one is time-like. So they have a bunch of different formulations. And what's interesting is that, these have a number of advantages, and so they were developed, like I said, in the early 60s, and then developed, then a big development again in the 70s and 80s, and then now with the holographic principle, people are working on them again. And so I'm putting data on a null surface, on this plane, on this hypersurface, and evolving forward to the next one. So if we use the wedge version here, and we just cut down a dimension, I'm putting data on that surface, and then I'm evolving. Proving initial, and I can prove. The interesting thing is I can prove initial value formulations to get data off the surface and get and so which is interesting. So I can push forward from the null case. And if you think about it for a second, it's kind of interesting because, of course, if I take a flashlight, I turn on the flashlight, it takes time for the photons to go out, right? So I've got, intuitively, it's taking time along there, but the production arrow, so let's think of a time arrow and a production arrow. And so what I want, again, in cases where, in the normal case, the production arrow and the time arrow they're in sync. And now we're thinking of cases where the production arrow and time arrow are not in sync, okay? Which I think is interesting so that you can get this teased apart. You might think of these as a kind of grotesque technical thing you can do, but there are many advantages that were pointed out in many different contexts. So one, it's a little bit closer to practice because you sort of see the past, you see stuff on the cone in cosmology. That's probably not such a big philosophical deal. But one of the big things is that, in the usual case, you've got all those nasty constraints on the spatial hypersurface. Here, those constraints go away more or less. They turn into really simple ordinary differential equations, which are solvable. And so, in some precise technical sense, this is more natural than the other case. And so, you can put the free data on these, and then determine points later. And So they have a whole bunch of different virtues, but I won't go into all the different virtues. Yes? Yeah, so I'm just meaning determination. Can I get it to determine the next state, or can I get it to determine some region? So here, so if I have a well-posed initial value problem, I'm determining some other region, the solution on some other region. That's all I mean. Yeah, so here, intuitively, it's taking time, for the photon, say, to go from here to here, when I turn on the camera, right? So it's finite speed of light, so it's taking time. So here's a case where I'm getting a difference between the production and the time. You see?
What's the difference between production and causality?
Nothing. Okay. Yeah. So if you want to, the way I put Thule's position was that the direction of causation gave you the direction of time. Here I'm getting a kind of divergence between those two, where they're getting out of sync. Okay. Now let's tilt now even further and go even kind of crazier. Can we put data, instead of our initial data, not on a null surface, but on a mixed time-like, space-like surface? So so one with signature plus plus minus, and then evolve into a plus direction. So if you like, intuitively, could I put data, on the wall for all time, just the wall, 2 dimensions of space, and for all time, take that data and get it to determine, say, can I evolve toward the east, say? I don't know if that's east, but let's say that's east. Can I evolve to the east? Well, then I would have, the production arrow going this way, but the time arrow would be going, orthogonally to that. Well, there's this really interesting corollary to Asgerson's theorem, which is a theorem in the study of partial differential equations. So if I have a second-order linear or quasi-linear equation, which encompasses a ton of physics, then the answer is no. If you put the data on a mixed surface, you cannot do this. So then the answer is no, which is very interesting. And I really enjoyed, there's a paper by Max on why is time one-dimensional, which is about this, which I just love. So one thought is no, you cannot do this because of this corollary to Asgerson's theorem, and so you cannot do this. On the other hand, sometimes you have to, sometimes you can't put arbitrary data, in the classical electromagnetism, in GR, you need to have, if you put some constraints on the surface, then the answer might be yes. Right? So it all depends on what you're allowed. And so what do I know on the yes side? Well, here I know 2 things. There's a paper by a philosopher and a mathematician showing that with a free wave equation, if you will allow temporally non-local constraints on this surface, then you can, for the wave equation, go this way. I also had so these are open questions, I think. I also had a conversation with Bob Garash, who works in general relativity, and I'll tell you, maybe I have 30 seconds, I can tell you the kind of amusing exchange we had where I asked him, can I do this? Can I go push off this way? And he wrote back, he said, Craig, I'm sorry, but for sociological reasons, we'll never know. The reason is that so much of the apparatus for proving a well-posed initial value problem is tailored to putting the data on the space-like surface, if you think of all the energy conditions and all of this, then no, he said, no one will ever do the work to be able to do it the other way, and so we'll never know. Then 10 minutes later, he wrote back and he said, never mind that, you can. And the idea, so he put forward this kind of conjecture that if you give me the solution on the surface, plus, and here you're cheating a bit, the constraint that there's a solution in the neighborhood of the surface. So in the neighborhood off surface, so I'm cheating because I'm not just restricting myself to surface stuff. If I have a solution off the surface, then he gave me this kind of, for the vacuum case, can I, then you can do this kind of patching argument that suggests that you can, which is really interesting. So in one sense, no. In another sense, maybe if you have enough constraints. Of course, I haven't added matter. I haven't talked about quantum mechanics. You can ask me about what I think about all of that. I don't know what the answer is here. I don't know exactly what to make of the null case. But what I do think is this, is that it's a win-win solution. It's a win-win thing to think about because either you can or you can't. If you can, then that really pulls the rug out of this production picture. So then you really, I think, get this picture of just this 4D world. Sometimes you get, solutions off from this data this way. Sometimes, you've got it off the null. Sometimes you're going, sometimes you're going off to the side. And it's just, and so if I were to look at the world and look at where the arrows of production are, there'd be a bunch this way, a bunch that way, and that's about it. On the other hand, if the answer is no, you can't do it, in some sense that might be right, or no, you can't do it so simply, well, then I think you've learned something deep about the difference between space and time. So either way, it's win-win, so I can't lose. So thank you.